Actually, before you disappear, I wanted to do to wish happy birthday to our TAs. They were born the same day, so they remind us one time less.
Amazing.
All right. So good luck with your presentation on the other side, and I keep here the audience enjoyed.
Right. Okay, great. Take care, everyone.
All right. Bye. Okay. So back to us, and I guess I'll keep I'll restart basically from the first slide that we covered today. And so let me share the screen. So yeah, both TAs have the same birthday. There was there was a birthday criteria to select them, perhaps, so we don't have to again keep in mind too many things. No, just kidding. It's not the first time. Also, in my previous lab, we had 4 of us had 2 birthdays, right? My birthday was the same as my coworker, and my previous advisor birthday was the same as another coworker. So this thing is kind of more common than you think. All right. So getting back to actual lecture class, right? Lecture topic. Class topic, whatever. What do we talk about today? And today we're going to be talking about, deep learning, but we start with convolutional networks, right? Why do I talk about convolutional net? Because, last lesson with Yann last week, we started with recurrent neural networks. I was thinking to restart to tell you more about the recurrent neural net today. I think I'm going to push that to tomorrow, since what Yann talked today is really, really connected to what I'm going to be digging further in this lab, right? So I think it's making more sense for me for you actually to listen, to hear more about the same topic, right? So we don't get too confused. So convolutional neural net, what do? They basically exploit the stationarity, locality, and compositionality of the natural data. This is what the first slide of today's lesson with Yann was about, right? And so he went perhaps a little bit fast on these 3 concepts. We are going to be building now some deeper intuition and understanding of what they actually mean, okay? Okay, so can I click here? Okay, fantastic. So input layer or input samples. What are these input data we use can be used for convolutional net, right? What kind of data is effective for being fed to a convolutional neural net? So usually until now, we have seen that our data points are those pink X bold vectors, right? So when they are bold, this guy over here. So if they are bold, they means it's a vector for me. And so I have the ith vector, X, belongs to Rn. So it's a column vector of n components, and this is bold because it's a vector. And so the set, so this is curly brackets, means the set of all the xi's of n components, such that xi is a data sample, is going to be my curly X, right? And so my curly X is the collection of training sample, of sample, right, that I have access to, okay? In this case, they are M. So my data set, my training data set, has M samples, 1 to M, where each of these can be thought, again, these vectors can be thought as a vector going from the 0 with the arrow, or you also can think about that as the point in this one point in this n-dimensional space, okay? But we can also think about some other type of data, which are a little bit different from this. So these are the input samples, right? So we can also think about the following, right? So my curly X instead, right now, are those made of the set of these xi's, which again are this kind of items, but xi's are functions now, okay? And so these functions, they go from this big omega here, capital omega, to RC. So the omega is the domain and RC is the image or codomain, okay? And basically this function are mapping my lowercase omega vector to a lowercase bold x, right? So it goes from vector omega, which belongs to capital omega, to the x, which is belonging to RC. And of course, this is a function, right, of the omega. And I have how many functions? I have m functions, right? With I that goes from 1 to m. So what is this omega? Omega is called the domain. So it's my signal domain. So x, this one over here, is called signal. And the signal has a specific domain, the omega, right? Instead, RC, these are the number of, so C stays for channel, okay? And therefore, the signals xi map my domain omega to the number of channels RC. Okay. So first question, what is this omega, right? So what am I talking about? Why do we need this, right? So we need this because if you try to just treat an image as one data point in like let's say you have a 1 megapixel image, right? A grayscale 1 megapixel image. So this means we are in a 1 million dimensional space, right? And you have one data point in 1 million dimensional data space. As I told you before, another data point is going to be very close to that one. And a third data point is going to be very, very, very close to that one. And so everything is very, very crammed together. And it's really hard to, I would even say it's impossible to train a fully connected layer, fully connected network. Well, it's also called multi-layer perceptron, but we don't like this word. It's impossible to train a fully connected network to perform, anything on this type of data, because it's way too crazy to move to operate in this million dimensional space. Because as I told you, we had to go in a higher dimensional intermediate representation. And if you start with 1 million dimensions, where do you go? Okay, it's not feasible in terms of computations, I think. And also in terms of number of samples that are required in order for you to train the system. Because the number of samples is proportionally increasing with the number of dimensions that are you're dealing with, okay? So I'm going to be getting there, okay? I'm answering this question in a second. Okay, so instead of having just thinking about images as data point, we want to think about an image as a function, okay? Which in this kind of context is, instead of calling a function, we're going to be calling it a signal. And so a signal gives us some information on top of this domain. So there is a domain. And on top of this domain, the signal will give us, some information, which is this our channel. And this is like, I call it a descriptive information. So for every location in the omega, right? So omega is our domain. For every location, the signal will tell us what is the specific information, characteristic information of that location of our domain, okay? So what is this domain, okay? All right, let's try to give you a few examples. So omega could be the order set of the going from 1, 2, 3, blah, 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 until capital T divided by delta T, okay? So let's say I have a sequence that is last 3 seconds. And perhaps I have a delta T, which is going to be 0.1 or 100 milliseconds, right? So the frequency, the sampling frequency is like 10 hertz, okay? And so overall, this set here goes from 1 to 3 and 4 until 30. And I start from 1 because that's how I count in mathematics. I count 1, 2, 3, right? If we do Python programming, we count from 0, or C programming. So my omega here is like it has discrete values, okay? It's not 1.2, 1.4. This is only 1, 2, 3. It's like an index. You cannot go in between. So it exists at discrete intervals, and I have a finite number of elements. So this is a first type of signal, right? And capital T is the total amount of time, of the total length of this signal, which could be like the 30. Like the 3 seconds I was mentioning you, that we perhaps do like some prediction with a predictive model. I don't know, this is something we're going to be seeing in the future. Or it could be an audio signal, like I want to listen to 3 minutes of of sound, right? And then the frequency, the delta t could be like, let's say, 1/20 kilohertz. Okay, that's usually a possible frequency, sampling frequency. Or 44, I think now we use 44 kilohertz sampling frequency for audio. And delta t is the sampling interval, right? 1 over the sampling frequency. So we figure now what is the this omega, right? The omega is the discrete index. We can index our signal, right? So we have x of lowercase omega, and then omega, lowercase omega tells us like a point. Like this can be also thought as a chain, right? You have one item after each other, or like a one-dimensional grid. What is C in this case? So if we are talking about, let's say, audio, we can have the following. So if it's 1, can you guess what is going to be the audio signal which has only one channel? What's called? You should be typing in the chat. It's a mono, yeah, that's correct. So this is a mono signal, mono type of signal. Instead, if I have 2 channels given a specific sample, what is called that? Okay, stereo. Someone else can also answer, okay? So yeah, that's definitely stereo. So someone that is not the same person here, can someone guess what is the 5 plus 1? Yeah, what is 1.1? Yes, okay, fine. Can we explain in English, perhaps, so that I understand whether you are following? Maybe we know already. Is it 2? Okay, 5 channel plus 5 subwoofer? No, 1 subwoofer, right? Yeah, one subwoofer. Yeah, that's correct. Yeah, so that's basically the Dolby 5.1. Okay. All right, so this is this type of signals are said to be one-dimensional because the domain has only one direction, okay? And that's called one-dimensional signal. 1, not 2, 1, okay. All right, so moving on, we can have this type of omega, right? This different type of domain. In this case, we have the Cartesian product of 2 discrete sets, okay? These are order sets, but okay. So you have 1, 2, 3, 4 h and times, right? So it's a like a outer product 1, 2, 3, 4 until w, no? And so as you can guess, h stands for height and w stands for width. Okay, so in this case, we don't have the unitary grid, but we have a 2D grid, right? The classical grid. And these are images, right? And so, yeah, correct. So let's see what C can be. So again, number 1, what is it? Someone that didn't talk so far. Please talk back to me. I know it's early. Oh, I don't know if it's early. Grayscale, okay, very good. Someone spells with the A, someone spells with the E. Okay, I prefer it British. Just kidding. It's not black and white. It would be black and white if the channel would be actually N, right? So you have binary 0 or 1. So you would have like 0 or 1 to the 1, right? In this case, I've written here R. And so R is going to be like all continuous values. So in this case would be grayscale. We would have to replace this R with a set 0 and 1, then you would have black and white image, okay? If black and white means salt and pepper, right? Like the binary image, right? Bitmap. Okay, so that's correct. Grayscale. With number 3, I guess you RGB, okay, you know, but okay. And then 20 is something also Yann talked today, right? I mean, don't cheat and check the slides before following the class, right? So they have to guess that. So the guessing part in the class is part of the learning, right? So the fact that you're not cheating on watching the slides that are already online, you actually can have like some better absorption of the material, okay? And so these are the hyperspectral images, yes. Sorry, okay, I was skipping this one. Okay, let me click further. For these are the hyperspectral images. And so these 20 bands are not necessarily a set. They are actually ordered. Like Yann said before, they are a set. they're not ordered, this number of channels. Actually, in the hyperspectral images, usually they are, and the lambda, the wavelength, are sorted such that you can move from one end to the other of the spectra. And they go outside the visual field, right? So that you can see all types of radiation or spectral radiations. And these are very useful, for example, whenever you have satellite imaging, in order to identify regions of desertification or potential fires and things, because each specific type of soil or ground type will have a very particular footprint, right? The spectral footprint, which is not that evident when you actually just use the color information, right? So given that we have sensors that are having like a input range that is much larger than our retina and our visual system, we can leverage that larger spectra in order to capture more meaningful radiation patterns, or even albedo, right? The albedo is the reflection of the light from the sun. Okay, the color image, right? I actually skipped the thing in between. So let me give you even a little bit more precise, understanding or explanation of what's going on, right? So my bold X, right? This body over here. So this is a bold X, means it's a vector, has a vectorial output. In this case, it's going to be 3 components. Is a function of the location W1 and W2. W1 and W2 can only take discrete values, and namely W1 can take values such as 1, 2, 3 until H, and then W2 can take values in 1, 2, blah, blah, until W, right? And so the width, W and omega, they are 2 different letters, okay? You need to put this curly thing in before, otherwise you don't understand what's going on. All right, so these are, just specifying a location in this 2D matrix. And then given the 2D location, you're going to be having like a vectorial, like a vector of 3 components, specifying the value of the R channel, right? The green channel and the blue channel. So the R channel is going to be a scalar field, is like a one-dimensional function. The image is a one-dimensional, right? The image, like the codomain, is one-dimensional. G, the same. This is basically a grayscale image, right? It has 1 channel, and the B is also 1 channel. But then if you put them together, you can have like the purple and the pinkish and the purple color, right? Here are my background, okay? Cool. So we have one more, and which is this one, right? And so in this case, the domain is the real axis, R4 times R4, right? So it's like a whatever space. I cannot even draw it and think about that. What are these? Do we know? Do we have physicists in class? So these are simply the space-time, and the other one is the 4 momentum. Okay, so we are talking about physics. So here we can use convolutional network in order to play with physics, and we can try, for example, to predict the, let's say, Hamiltonian of the system, okay? Okay, so we can do fancy things here. And this is like the type of data we can use convolutional network for, getting actual, stuff to work, right? So, and let's actually start simple, and let's say how this 1D signal work, right? So this 1D signal, I sometimes also write it as like a lowercase x with square bracket. And inside there is this k, which is my indexing variable, right? Which should have been the omega in the previous slide. And again, this can also be considered like this big long vector of these specific items happening at specific locations, right? And so there is no intermediate value. Okay. So we mentioned that we can apply neural nets, convolutional net, if the data has some specific property. And we're going to be covering this right now. So once again, the 1D type of signal are those in which the domain is one-dimensional, right? So the omega has goes in one direction. And so this could be like, for example, the waveform here in the first example. The second case, we have like a grid that goes in 2 directions. And so it's still discrete values, and we go in two directions. So it's a two-dimensional image, a two-dimensional type of signal. And the third one is a one-dimensional signal where each item in the sequence is corresponding to these x1, x2, x3, which are very long vectors. And let's say these are, so each of these x1, x2, and x3 are 10,000 dimensional vectors representing the index in a dictionary, representing where this specific word happened to be, okay? So John maybe is the blah word in a given dictionary. So the collection of these indexes can also be thought as, a signal that operates in one dimension. Okay, so let's focus now on the first signal, the one that goes in one dimension, and it is represented here with a waveform. So this waveform here, let's zoom it a little bit. So on the first part, I can see this specific pattern happening on the early part of the signal, okay? Later on, in the same signal, I will also see the same type of pattern. So this is one characteristic of this type of signals, these natural signals, is that similar type of patterns happen over again, okay? So patterns are happening in different locations of the signal, the same type of pattern. Moreover, let's zoom it a little bit. Yeah, there we go. So question for people at home. If I see a peak on the left-hand side, how likely is that I see a peak coming up quickly? Or if I can quantify this better, how likely is that a peak happen very quickly after a first peak rather than further away? Or even further? Or what is the likelihood that given that I have a peak on the left-hand side, there is a peak there or even further away? So we can tell that, perhaps if I say a word is make like of a sound, and this sound, which is called, there are phonemes that are attached together. If I want to say a specific word, like the word, it has actually one type of structure. And this structure, if I say multiple times, will always be, having this information condensed in that specific temporal interval, okay? It can be a bit larger, slower, depending on how fast I say the word. But again, as you figure, I said this specific word so many times that it appears several times in the overall temporal information, the temporal domain. And then the actual likelihood that you find a specific phoneme after another phoneme is very high, right? Like very close together in time. But then afterwards, if I say something else over here, it's quite decorrelated by the fact that I have this specific pattern happening over here. Nevertheless, you observe the same pattern over again, and then there is some type of local structure that is in the signal, okay? So there are two things over. What I was trying to say is that, again, the information has a strong correlation in local regions, and then it happens again and again. This does not only happen for the audio type of signal, as I show you right now, but also for the second type, the two-dimension, right? So let's look at this little cute kitty here, and let's zoom it like in the central region. And then you have like, a monster. No, it's huge. Okay. All right. So in this type of image, signal, you also can see now the discrete locations, right? So these are called pixels. In the other case, with the audio, they are called samples, but they're same thing, right? Like in 3D type of data signals, you're gonna have them called voxels. But again, all of these different names are just saying that there is a unit element, like the value associated to the unit element in the domain, right? So the first point was that let's look at this, crevice or whatever this type of pattern we have by next to the eye. We can observe that type of pattern, it's similar to this other one that happen also further away. Again, we can see that similar patterns reoccur across the domain. In this case, it's two-dimensional domain, right? over and over again, right? So we have this property that I'm going to be called it stationarity, okay? So stationarity is that the same pattern happen again and again in the same type of, or in the same domain, right? Over the domain. Nevertheless, the other property we were mentioning is the fact that, so how likely is that given the center of the pupil is black, you're going to be also finding another pixel nearby that is also black? I would say it's quite likely. You have a high, degree of probability. You have a high degree of likelihood that you're going to find another black pixels in the pupil, right? In the hole of your eye, because all the pixels within the pupil are, not reflecting the light. Otherwise, you wouldn't see anything, right? So it's a hole, and the light goes inside the hole. You don't see anything because there is like a chamber behind, right? Nevertheless, if you move further away from the pupil, from the hole, and you move to the iris, then you're actually going to see, there is some color behind, like nearby the pupil, right? So it's less likely that also the iris is black. Could be if you have black irises, you could also have that like it can be the same color. But now let's take a step even further, right? So that's completely outside the ocular area, and the likelihood to find another black pixels, unless you have a black cat, it's rather low, okay? And the further you go, the further away you go, and the less likely you're gonna find some, likely similar value, right? Or you have, So again, the information has some, the information in the signal happen to have like local kind of property, has a locality, and then the similar type of patterns happen again over the domain, and that's the stationarity. So we need the third property, right? Let's see who remembers that. So I don't know if you had breakfast or not, but here I'm going to be showing you some donuts, okay? So here there are many donuts. There are the chocolate, there are with the strawberries, there is some with the, what's called the blueberry, and etc. Okay, so exercise for those of you in class who wear glasses, okay? So you can raise your hand so I can actually see that. How many of you, if you should raise your hand, how many of you wear glasses? I see a few people. Okay, just 6 people. What about, so everyone has a perfect sight? No, okay. So 10 people. Okay, 12, fantastic. Okay, now those people that are wearing glasses, please take off your glasses and look at the screen once again. Now you can also, okay. You can also react with that. Oh, usually this works very nice in class. Yes, okay. Among the people that don't wear glasses, do you know what's going on here? No. Okay. Oh, very good. Okay, so someone please explain who cannot see what's going on here. So if you squint, if you don't wear glasses but you squint your eyes, just squint a little bit. Yeah, that's Marilyn Monroe. Okay, you squinted. Very good. Okay. So this is the third part, right? So this is compositionality. The part that if you look at very close by, you don't see any specific type of major structure. As you start, gathering and integrating the information, in this case especially, you will be obtaining some, structure, like some meaning out of these individual specific values, okay? And so, as we can see here, there is a high local, or go back at a distance, yes, or just remove your glasses if you're blind like myself. Again, here you can clearly see there are there are very many chocolate, what's called this stuff? I forgot the name, not donuts. Are these donuts or, let's call them donuts. I don't think they are bagels, right? The bagels or donuts, whatever. They look someone look like donuts, some like bagel. But anyhow, you have like chocolate, oh, someone see the lips of the face. Okay, very good. So the lips of the face are those pinkish one, the red one, right? So these are like strawberry donuts. And you can see, the fact that you have a strawberry donut here will have a very high likelihood the fact that other strawberry donuts will follow. Okay. Similarly here, you have, a brown chocolate donut. You have many chocolate donuts nearby. But the farther you go, and the less likely you're gonna find similar donuts. Okay. And then if you put all together this information by integrating over the spatial domain, or just going further away and squinting your face, your eyes, you can see how the overall local structure can give you a overall understanding of the entirety, right? And so when you say, oh, this is a face of a lady, that's the whole entirety of the togetherness of all this specific local information that gives you that kind of overall cumulative information. Okay, everyone can lower your hands. You still have your hands up. It's going to be, the blood is going to be going down your arm. All right. Okay, so moving forward, we have already seen how fully connected layers work in the just last lesson, so I'm going to be skipping this part. And then I'm going to be going directly to the, okay, maybe I can just show you the slide. So this was how we compute these specific values, right? You remember that this animation from last time, right? So we have that each neuron here look at every other neuron before, and these weights are used in order to weigh the input neurons, right? So given a specific neuron here, the first one here, this one gets the summation of all these guys here, weighed by this coefficient that is stored in this connection, which is again then stored later in this matrix over here, right? And then we apply possibly a nonlinear function. As you can tell, there are too many connections. There is a huge amount of computations. Given now that we know that natural signals have this specific type of properties, the 3 properties, which are typed down on the chat, we repeat them a few times. Help me remind them. What do we have? There are 3 properties. We mentioned this like 7 times or 10 times so far. Tell me, type in the chat. No. Okay, locality. Second one is the fact that things happen over again in the same manner. It's called stationarity. And then the third one was the one I show you right now, the fact that the meaning overall comes from this compositionality, this hierarchical combination of individual stimuli. Okay, so now we're going to be combining or exploiting these properties in order to introduce some inductive bias in the architecture in order to be able to remove computations and speed up convergence of the learning algorithm. Okay. And so now we're going to see how locality can induce sparsity, or, we can use sparsity given that our signal is local. What does it mean? So in this case, I have the pink layer, and my input layer is going to be the layer L minus 1. Then I have my layer L, and then, the following one is going to be the L plus 1. And then when we have, the fully connected layer, we have that each input is weighed by this coefficient stored in this connection. So we have here 5 connections, right? We have 5 connections. We have 10 connections. Overall, we have 15 connections. And then on the other side, we have, so here's our 15. And then on the other side, at layer L plus 1, we're going to have 3 more, right? So we're going to have, this total amount of connections, right? 18 connections. So I cannot count in English, sorry. Okay, but now we know that on the other side, our signal is local, right? So the information is just present in a specific region of the domain, right? So the domain here is 1, and it goes in this direction. So this neuron over here, it just cares about checking for patterns that are happening within a small region here. We don't really care to know what happens here or here, because the further you go away and the less relevant these neurons are, these pixels or samples or whatever you want to call them, voxels, right? And so the first part is going to be, I'm going to just use 3 connections, right? So just look for specific patterns there. For the second neuron, I'm going to just look at 3 patterns over there. For the third neuron, the same. And so here we have 9 connections. On the right-hand side, we still have those 3 connections. So in total, again, we have 12 rather than 18. Okay. If you increase the number of neurons, you're going to see how these numbers, increase and how they compare. As you move from the left-hand side to the right-hand side, you go high in the hierarchical view. So these networks are usually drawn or left to right in this case, or actually I should have just drawn them bottom to top since I actually have space here, right? Why do I draw them bottom to top? Because that's how you go up in the hierarchy, right? So the network should be in the same direction where you climb from the base, where there is the input, to the higher level of this hierarchy, right? And so I'm going to be defining something now, this RF, which is the receptive field, okay? And so my receptive field here is simply telling you how many neurons my given neuron can see from the previous layer, right? So in this case, the receptive field for the output neuron with respect to the hidden layer is 3. So question for people at home, what is the receptive field for the hidden neurons with respect to the input neuron? Type 3, okay. That's good. So final question, what is the receptive field of the output neuron with respect to the input? 5, okay. I don't know if you're checking the slides in advance or you're just reasoning along with me. I hope you're reasoning with me. Okay. And so the more you go to the right, the more you have this global view. And similarly, as you figured before, Wi-Fi, because you can count that this body here, this blue one here, can see up to 5 pink input. There you go. Yes, thank you for answering. All right. And so again, in order to actually be able to, let's say, classify the previous image as a face of a lady, you need to have several layers in this case, right? You can't really do it with one layer. Or you can have several layers and then you need to reduce again the number of the information, right? Which we can do this, for example, with a pooling. We're going to see that in a second. Okay, so here, how is made a neural network, right? So we have 2 things on neural network. We said, remind me, we saw that last time. We have, what's a neural network made of? Type in the chat. Yeah, linear layer, but this is my labs, right? What terms do I use? No, squashing, okay. And the other one was rotation, okay. So we have rotation and squashing. And the rotation is simply, a fine transformation, like in proper jargon, and which is, achieved by doing a matrix multiplication, right? Matrix multiplication plus the displacement, the offset. And so in this case, I just show you that we start with a fully connected layer, which is a matrix. But in this case, I'm showing you I'm dropping some connections. So this dropping connections simply means writing zeros in correspondence of all the connections that are not existent, right? So in a next lesson, I'm going to be actually writing down the math to show you how this works, right? But nevertheless, the convolution is still a matrix multiplication, a linear operation, right? Just with a lot of zeros, and that's when you put a lot of zeros inside a matrix, that's called a sparse matrix. And so that's why, again, that's where these sparsity terms comes into play. But again, still matrix multiplication, still a rotation. And also it needs to be a rotation in a high dimensional space, right? So these convolutions will have to, rotate your data, and then it just looks at these specific regions and expands them to multiple hidden representations, right? But it's just that small region. You cannot take the whole thing. It's too many points, too many, it's a too high dimensional input otherwise. Cool. Second part, stationarity, which implies parameter sharing. What does it mean? So in the first case, I show you, we start with these sparse connections on the left-hand side, where all these arrows are white. Instead, I just show you with a dashed gray line the connection we dropped, and which are no longer with us. Okay, so those are zero connections. On the right-hand side, I'm going to be drawing the same thing, but in this case, I'm going to be using colors. So I'm going to be drawing the first edge in yellow. And so all these ones are going to be yellows. Similarly, I'm going to be drawing all horizontal connections with the orange color, as like this. Finally, all the final connections are going to be drawn in red. And so these are going to be my three colors. So these three colors are basically representing the same weight. So given a neuron here, the neuron that is one up will be always multiplied by the yellow coefficient. So this neuron here has the neuron up, one up multiplied by the yellow coefficient. Similarly for this one, okay? So they all share the same parameter, right? That's why it's called parameter sharing. And then I collect all these values, the yellow, orange, and red, into this collection, which is called a kernel, okay? So we have first, definition, the word kernel. And so parameter sharing allow us to have quite several benefits. First one is faster convergence. Why is that? Because the same weight actually can be getting gradients from different regions. Before you get, that this specific value here gets gradient only from this location. In this case, you get this yellow one gets gradients from multiple parts. So you have much more information for moving faster the way to the best location. You have better generalization because you're not looking for a specific thing that happens in only one location, but you try to find a more general type of pattern that can be used all across the domain. Okay, so doesn't specify too much for that specific region. It's not constrained to the input size. This is really important, right? If you make the input a bit larger, even after training, you already have the weight that can be used to tackle that extra part, right? So what happens is that you can train, let's say, a face recognition system on just faces, like my face here, and then you can apply this on the whole image over here, right? And then you can just apply the convolutional net all across this, big image by having it train only on this small type of input data, okay? And there is no issue with the larger input, right? Instead, if you consider this big image as just one big vector, then you have no idea how to, tackle the fact that you have more pixels now than what you use for training, right? And so this is something that, is not to be taken, not to be forgotten. Finally, the kernels are independent. So if you have multiple kernels, you can compute these convolutions, these multiplications, by multiplication, I'm saying matrix multiplication, in parallel, right? They don't share any type of, they don't have dependencies. You can compute all of them together. But here we just saw one kernel. So where are the other kernels? I'll tell you in a second. The connection sparsity instead basically reduce the amount of computations. You can implement a convolution with a matrix multiplication, which is basically, having a big zeros inside the matrix, but multiplying by a zero, you know already what's the answer, right? Nevertheless, having the convolution implemented as a matrix multiplication can be convenient if computation is free to you, right? So let's say if you use a GPU, right, a graphic card, you have a given amount of computations you can take, right? And matrix multiplication are already implemented very well. And if you can take this larger amount of chunks of memory and you still have that amount of computation, you can just use them with a classical matrix multiplication, and they're perhaps gonna be even going faster than running the other option that goes, throughout the whole thing, right? So in one case, you just do one matrix multiplication. You're gonna go faster, but it takes a lot of memory as well. The other one is going to be slower, but perhaps it takes less memory. Given that you have a larger budget of computation, you can still use. Connection sparsity equals tried. No. Connection sparsity means you have zeros in your matrix multiplication. So the matrix that you're going to be using has some values set to 0, which are these dashed lines. All right. So we mentioned before we had kernels. Let me go into these kernels a little bit more. So in this case, we said that we have the yellow, orange, red kernel that is applied to the first triad of input. Then it's going to be applied to the second triad, and then the third triple, not triad, triple of neurons. And so these one are going to be stored in this collection here. So my kernel, in this case, has 3 values, yellow, orange, and red, and they are stored in this vector over here. Nevertheless, I may have a second kernel, okay? And so I have the kernel blue, purple, and pink. And so for this specific case, I have 2 kernels, each of which has length 3, okay? So the kernel, no length, sorry, my bad. The kernel dimensionality is 3. It has 3 items, right? And I have 2 of them, right? How does it work? So by the fact that I have 2 kernels, by running the first kernel, I'm going to get the first set of outputs. By running the second kernel, I will have the second number of outputs. And so you can think about these neurons over here. Oh, my bad. But you can think about these neurons here as having 2 layers, the one on the screen, and then one layer out of the screen, right? So you have one, this is on the screen, when you apply the first kernel, you have the first output. And then you apply the second kernel, you're going to have the second output on top, right? And so in this case, we move perhaps from a mono type of signal, if these pink guys have only one value, to a stereo type of, hidden layer, okay? But in this case, instead, my input, it's a 7-dimensional, it has 7 channels, right? So each pink circle here are basically 7 stacked circles, like 1, 2, 3, 4, 5, 6, 7, right? So there are 7 circles one on top of each other. Don't write private messages. I cannot see them. Just write to the public chat, so also the TAs can answer. So you have 7 input. Sorry, you have 7 channels in the input, and then with 2 kernels, you will have 2-dimensional output, right? Usually, if you're going to be using a stereophonic type of signal, you're going to have just 2 channels in the input, and then perhaps you want to bump these to 16, let's say, intermediate channels for the hidden layer, right? So you want to usually upsample, right? You want to go in a higher dimensional space when you move to the hidden layer, such that things are easy to move, as we mentioned a few times already. Okay, I'm talking too much. So the fact that these input are 7-dimensional, like basically the channels are 7. This means that this yellow item over here, it also has 7 components, okay? So the yellow star, the orange star, and the red stars, all of these are 7-dimensional vectors, okay? Again, coming out from the screen, such that I can perform the dot product, the scalar product between this and the input. All right, so my kernel size are going to be the following. So I have 2 kernels, you can see over here, of which each element inside of the kernel has 7 dimensions, and this is the 7 over here. And then overall, I have 3 items in this kernel, 1, 2, and 3. Right, so it has to be 7. It has to match this dimensionality, such that each value in the vector input has its own coefficient, and then the 3 is the actual length, the actual span of this kernel, right? How much the actual dimensionality of it. I don't consider 7 as the dimensionality. 3 is so the 3 is how how much you cover of the domain, right? So the 3 is going to be telling you cover 3 samples of the domain, and 7 has to be the number of channels matching the whatever source, right? You have to be able to weigh each channel with its own coefficient. So 7 is given to you by the previous layer, which is again the number of channels of the previous layer. 3 is going to be the how many components you basically want to consider in your domain. So this is a parameter that depends on the locality of the signal, right? So if you have signals that are more spread, you want to have a larger number over here, right? Such that you can check for larger type of signals, right? Larger, more extended type of signals. Number 2 here is how many channels the next layer will have, right? Okay. So in this case, one-dimensional data uses 3D kernels collections, right? So 1D data, because it goes only in the domain is one-dimensional, right? It has these kernels which have 3 dimensions: number of kernels, the number of channels, the extension in terms of domain. Padding. So what is padding? Padding is necessary when you want to actually have the same dimension across the network, even though you apply a convolution. As you can tell here, I apply a convolution with a size 3 in this case. The size is again the domain size. You have a reduction of the output due to the fact that you apply this convolution, and so the reduction is going to be equal to the size of this kernel minus 1, right? So the size is 3, and therefore you have 1 is missing over here, 1 is missing over here. Okay, you can see this, right? So how much do we need to pad? We need to pad one extra thing here and one extra thing here. And how do we get there? So you number of 0 padding, it actually is equal to the number of kernels minus 1. And then we're going to be doing half of it on one side, usually one half on the other side. Usually that's why we like to have odd numbers for the length, for the extension on the domain, right? So for this number here. Also, the other the reason to have the odd number is that a given neuron corresponds to a given location. If you have a even number of edges here, you're going to have that one neuron corresponds to 2. And so you're going to have some blurring factor. Here you can also just copy the information over, right, to the same location. And so we need 1 extra input per side. And so I'm going to be inputting a 0 there and a 0 over there, such that now I can perform a convolution there and I get 1 extra there and an extra there, such that now the number of neurons in the hidden layer are the same as the neurons in the input layer. And this is helpful for, not getting crazy with varying size of the network. But arguably stupid because you insert, some 0 information on the edge, which was not there, right? So we add something. All right, so how do we actually use, can we use different type of padding? Yes, you can do that, but usually you're going to be having 0 mean, right? Anyway, and so a 0 is a good value to use for these edges, right? So you usually with 0 mean the input, and you divide by the standard deviation. Also, whenever you use like the batch norm or layer norm, you're going to be always having the average value is going to be 0 for each layer, right? So adding a 0 is not too bad. By convention, each kernel with 1 channel will have an odd size due to this. But we like to have odd numbers of extension, such that there is going to be a central location, right? If you have an even number, there is no central location, and that can create blurring effects. So here is a little bit of a practical, suggestion about how to use these convolutions. which is going to be represented in this diagram. So you want to have multiple layers such that you can create this hierarchical structure of convolutions, which are these rotations, nonlinearity, which are the squashing. We have perhaps to use some pooling factor, right, in order to reduce what is the spatial dimensionality. And then batch normalization, it's something that it's been introduced and now it works like magic. Basically, it allows us to actually train very long networks without having issues in convergence. We also found out that residual bypass connections are really important in order to get a network to train very well, even if it's very, very deep. And so what the network does is basically converting this input, which is very, very flat in this case, no? So it has the thickness is very tiny, but the information is a spatial information, right? The information is distributed across the domain. And so I usually call the thickness as the information on the thickness as characteristic information. So a given location has a specific characteristic. In this case, what is the characteristic information of a given location in this pink image here? So what do you know about the specific location? You know the color, right? So the RGB is the specific characteristic information of that location, the specific pixel. On the other side, at the end of the network, let's say we do classification, we have just one big vector. And all of it is characteristic information. There is no more domain, right? We just collapse everything in one specific thing. And then the given location in the actual across the vector is going to tell you, this is a hippopotamus versus a giraffe. And in between, you have basically a tensor, whatever size that is, a midway between very thin to very long. And so the network basically changes the size. You have like a reduction of the domain information, and then an increase in this, a characteristic information. Pooling, that is the last part. Then we're going to be covering the notebook. Basically, we start here with an edge of this, in this case, a two-dimensional signal. And we have also it's called kernel, which is the area where we look at. In this case, I have an even number of items. And so I look at what is, a possible, operation that is summarizing the content. And for example, I can use the LP pooling in this case, whenever I consider the P norm, or I can consider the max pooling if I consider like P goes to plus infinity, right? And so I apply this LP norm, which is again condense the information, or if I use max, actually throws away information, more or less. And then you get one value. And then I apply a stride, such that I can decimate the information across the spatial, across the domain, right? And so this allows me also to reduce the amount of computations. Similarly, you can do something similar with a strided convolution, where the convolution is applied only at jumping intervals, right? And then you don't consider exactly what happens exactly all across the domain. And so in this case, the number of channels stay the same, right? Because you perform only the pooling across the domain coordinates, but then we keep the same number of channels. That was pretty much it for the slides. So in the last 10 minutes, we're going to be covering the notebook. Again, as I was mentioning, I think on the chat, or maybe not, I forgot. We always keep open a terminal where we can, use it, run it as a calculator, right? Anyway, so okay, the bar is in front of my nose again. So let's move the bar. Let's move my face. I cannot move my face. There we go. Okay. So we go in work, GitHub, PDL, okay, and then we do conda activate PDL, and then we do Jupyter Notebook. Okay, and so right now we're going to be looking at the convolutional net, right? So just for sake of, we switch PyTorch to deep learning, set kernel. So I'm gonna just execute everything, and then I'm gonna be commenting while my computer is running. Okay. So what do we do in this kind of notebook here? Let me go full screen. Okay, there we go. And let me zoom in. Okay. So here we implode some plotting libraries, and we set some default visualization things, right? Import torch, and then we import the NN package. Also, I import some other data set, and then pyplot as PLT. Here I just have some handling function, like helper functions, and we set the device to be whatever is available on the current platform. I have a CPU in this case. Here I load the mNIST dataset. This is the modified NIST, which Yann modified back 30 years ago. And then we apply some normalization, which are computed across the whole training set. So these are going to be the mean, and then we divide basically by the standard deviation. Here we have that I'm going to be plotting you 10 digits, right? And so here I'm showing you with yellow numbers that are basically close to 1, and then purple numbers that are set to 0, okay? But then since we average, like we remove the mean, I believe that the yellow is going to be +1 and the purple -1. So in this case, we are going to be using a different type of function, okay? I have like a different type of neural network. Last time we saw that we can use sequential. In this case, we're going to be using the more extended version of the building a neural network. It's more a flexible way of building a neural net. So in this case, I have my class, which is going to be a fully connected 2-layer. And then I have my init, which you're going to be inputting whatever parameters you want to pass later on. And then I have like, I assign to my internal variable like input size, the input size, and then I define my network, again in this case, to be also sequential, but this is defined inside this init function. Afterwards, after this is initialized, I have to define the forward function. And the forward function simply does the following. It gets the input and it reshapes it in one big long vector, because this is a fully connected layer, so it doesn't know exactly how to deal with anything that is not a vector. And then I simply feed my x, my reshaped review, right? This one big vector to this network, right? In the other case, instead, I use a convolutional net, and I don't use this sequential, right? So here I have each individual item to be like the separate thing, like the separate module. And so I have a convolutional 2D. These are in an n.package. So I have a capital C. Capital C means this is an object, and this means inside there are all the parameters, right? All the weights. Similarly for this NN capital linear. Here we are using NN ReLU and as a object in the NN package. Instead, in this case, since we are going to be using the extended forward, I have that I send the x through this conv1, and conv has a lowercase in this case because it's just a function, although this one gave us also the weight. And then I get the ReLU from this f, the functional. And so ReLU now is just a function that doesn't have weight, so I don't need to use the NN package. So the NN was giving me a module, and it's necessary whenever you use the sequential because you have to stack several modules. Here I just apply my function to a given input, right? So here I apply all them one after each other. You can do this, or you can just do the sequential, right? How much time left do we have? Where is the timer? Okay, I don't know the timer. I think we have a few minutes left. So here I'm just creating these two networks such that they have the exact same number of parameters. here I have my training loop. And then what I do is going to be the following. So I may or may not permute my data points. So let's see what's going to be. I train my data, my networks here on first the normal data set, and then I try to change the order of the pixels just to see what's going to be. So we're out of time. Okay, I'm finishing up. So I'm training here the small fully connected layer, and the number of parameters are 6,000, and we get 96% on the training set, and then 87 on the test set. Then I train my convolutional net on the same number, on the same type of data, and we also have the same number of parameters, right? 6442. Here we have 6422 is similar, right? And then we get 95, right? So we can see here how the convolutional network has a better, accuracy on the test set than the fully connected layer. But then here I'm going to be shuffling the pixels, and so I just take all the pixels and I apply a deterministic transformation. Whenever I apply a deterministic transformation, I get the following, right? So instead of having this type of 5, the 5 is going to look like this. Instead of having a 0 that looks like this, I'm going to have a 0 that looks like this. Okay. The 4 looks like this. The 1 looks like this. Cool. So now I train the ConvNet on this shuffle data. And so we went down from 95 to 83. Why is that? Because now there is no more local information, right? Because we completely screw up the type of data. Instead, if I train the fully connected layer on the same type of data, we are not going to be observing such, worse performance. You see 85 here, and before we also noticed that was what 87. Okay, this is just statistical variations. And so if we put all together, and we see how the cumulative, how the two things compare, we have the following. Let me unzoom a little. So the fully connected layer before was, performing this much well. The convolutional net was performing much better. Now, after scrambling the pixel order, we have that the convolutional network performs much, much, much worse. And then the other one should be performing roughly the same as before, right? There are no differences for the normal neural net. Okay. Why has the neural net reduced? Because of statistical variations in the initialization of the parameters. If you can try again. Maybe this one can be better than the first one. So the fully connected layer doesn't see any type of difference, and the variations you get are simply the normal expected variations in performance that you may get when you run multiple times the same training procedure by using the different type of different initializations, right? So this is just due to statistical, fluctuations. Instead, in this case, the convolutional net really drastically lost performance due to the fact that those little kernels cannot really look at things that have been moved around. So there is no more way of extracting information, given that there is some information still extracted because we have several layers, but nevertheless the kernels are less effective, right? Because they have a limited view, and then we move pixels away, and so there is no more way to capture that kind of information. And that was pretty much everything I want to tell you about convolutional network for today. So tomorrow we meet, and same time, 9:30, and we're going to be talking about recurrent neural network. And these two lessons are going to be, I think, quite helpful for the homework that is going to come in out tomorrow. Okay. I think that was it. If you have more questions, ask them on CampusWire. We will answer every question you have. I was not checking the chat for the last few minutes, such that I don't waste too much of your time. Okay. All right. See you tomorrow. You have a nice day. Bye.